responding. So let's create a new project. And since we already know how functions work and how memory management works and all the other C things, we can now take a look on how in C++ one would go about representing strings. So let's create a project strings. Okay, let's maybe rename this to main, since the name strings is often used for libraries and stuff. So as you might have remembered from previous lectures, I'm sure I already mentioned that things like arrays are not natively handleable by the CPU. The CPU can only handle integer types, floating point types, to some extent with special instructions, some vectors of defined lengths of the aforementioned types, but it's not capable of handling natively arbitrarily length data. And a string, as one can easily surmise, can be arbitrarily long, at least in the first approximation, and is also very important in computing. You want to be able to write some text to the screen. You want to be able to handle file paths. Um, you want to be able to get text input from the user. Some programs are even made to especially to handle and format text, like the IDE itself. Um, and thus it is necessary to be able to handle strings um, as conveniently as possible. And C later has its own strategy of doing it. It is called a C string. It's null terminated. So basically, a string is a array of type char, so signed byte. Meister. We can use an array of undefined length here, and then we can assign a string to it. Let's say test123, and this is a set just an array of chars with those chars, and then there is a zero value appended. So the text, the letters that you see here have the ASCII values. So something like 0 is not 0. If you want really 0, you would need to use the integer value of 0. So let's take a look how this looks um, in detail. As we know, the typical way how until now we have been initializing arrays was using this curly brackets, and then we just provide the individual integer values. And the 0. So those two are exactly the same thing. they're they end up in memory being identical. So the 0 here is always automatically added by the compiler when it compiles, and the 0, the integer 0, indicates the end of the string. So this character cannot be used as a part of the string normally. Of course, you can, since this is not hardware backed as a mechanism, you can in principle invent your own string, define a different character as terminating character, or what also is done often if you want to have a more fail-safe mechanism is that you just use an array of characters, and in addition a second variable containing the length. Obviously those two you would pack together in a struct so that they are always associated, and then this adds an additional level of safety and reliability. In fact, such a non-standard string is what is used by the Windows kernel and the NT APIs in general. We will take a look on this at the end of this chapter, let's say. So let's just quickly get the sizes of those two strings to really see that they are the same. Const int meister size is equal. Then we do the same for our other one, and we see that both end up with 9 characters. And as we see here, we have 8 characters used, and the ninth is the terminating 0. The approach with the terminating 0 is very convenient because you only have to pass along one memory buffer. You don't need to handle structures, etc. But it is also dangerous because you don't, when you pass a buffer with a string to a function, unless you also specify its length in an additional argument, the function doesn't know how large the buffer is, so it could easily write past the allowed memory range. Or if you have the null termination and you get somehow a memory corruption, then the null goes away, and if you are reading the string, you reading and you keep reading until you run into some invalid memory. So um, while it's convenient, it is not considered really secure. And nowadays, of course, when writing modern code, you would either try to use some custom type like it's done by the NT API in Windows, or you would just use a more complex C++ object which represents a string. On that we will take a look a bit later. Okay, so another way to so these strings here are allocated on the stack, and the content of the strings is copied into them. So you can modify them, you can work with them. The memory where they are is writable. Of course, the length is limited. If you would want to add some text, we could of course just make it allocate much more memory, then we would have enough space to write, to append something to them, etc. But this since this copy is always the content, it is not quite in every case the best option. If you just want to have a constant string, you can just create it like this. And what we are doing here is we're creating in principle, instead of an array of chars, just a pointer to a char or an array of chars. And what happens here is that this will point to this string, but contained in the executable and not writable section of the application, or in a data section, depending on how the compiler lays those things out. Usually such sort strings get packed together with the executable code so that they can be accessed without having larger offsets, which makes the code in total a bit smaller, since you can use opcodes with a shorter range and which consume less bytes in the encoding. So in such a string we cannot write. If we would try to write to it, it would crash, because as said, we just get here a pointer to a read-only array inside the program memory. And here at some internally such a string in the read-only array also exists, but here it is explicitly copied. So we can put a breakpoint here and take a look how this is implemented. So here basically we load the address of our array on the stack, then we load into AX, then we load the address of the constant string that is somewhere inside our application a bit further away into RCX. So we can step through this. Now if we go to the memory here of RCX, we already see it contains here the test123, and then we see it contains other strings. So in this case the compiler chose to put all the data into one data section somewhere else, not to put it into the program section itself. And then we use the mechanism which we have already seen when we were handling structures, where we initialize special registers and then use this rep moves to just execute this move operation, in this case 9 times, which copies all the bytes and then is done. So it's a reasonably efficient approach. If we define a string like this with every byte individually, we see here that the data really is stored as instructions, and you have individual move operations setting every single character inside of your string. So this of course arguably is much less efficient, and we also see how much more opcodes it uses. It uses like for opcodes per line, 9 opcodes here, so it's like 30 something opcode characters that are used, while here we need much less bytes. And of course, if we would have a longer and longer string, then this would become more and more favorable. Our strings here are rather short. And then of course the last option here, we see that this assignment is the shortest. We just load the address and write it into memory. So when we arrive here, we can see that at Rax we again we pointed here, and apparently the compiler was smart enough to, since it saw the same string being used multiple times, to just save it once, and then those two initial values are really located at the same memory location, so this is convenient. You might remember from the previous lecture about memory management and protection that in principle, if you would want to modify it, we could change the page protection to allow writing and then write to it, and this would change of course the behavior of a program and the string for all the subsequent calls. But of course this is more an unelegant hack, so we of course don't want to do that. And like with every array, when we have a string, we can just assign individual characters, individual values in the array. Let's for example replace the fourth entry with an underscore. So at this level, of course, this is quite tedious to work with those strings. For example, if you would want to know the length of the string, we cannot easily do that. We need to count it. Int mylen is equal 0, and then we make a loop for const char ptr is equals my string asterisk ptr is not equals 0, ptr plus plus mylen plus plus zack. So of course this also is not quite something. So as you see, it counts 8, so it counts the length, the actual length, not the actual size. So the terminating 0 is not counted into the length of the string. But as you see, this is of course kind of not convenient. So obviously, since strings are so important, since the very early days of C++, of C and even before C++, there are quite a few built-in functions into the C runtime, which help you with working with strings. Let's include a few things. And this we need during this section. So of course, instead of counting the string, let's say by hand in quotation marks, we can just string is equals to len, call a function that does exactly this for us. Let's pass the other string to it. The thing will internally execute exactly the same operation. It will just loop through the string until it finds 0. It might try to do it in some more effective ways, like processing larger chunks, since here we are really working byte by byte, and as you know, a 64-bit CPU can work with 64-bit integers, so with 8 bytes at a time. So the developers of a runtime might decide that it might be more efficient to try to look in larger byte sections for patterns. Although with string length, this is rather unlikely. It's more likely to find such optimizations for memory copying and functions like this. How much you can optimize this really depends on the available opcodes. So we will not be diving into those details in detail. And there was one more thing we should do. Since this kind of is not necessarily safe, because we could, for example, forget to add this 0. So let's do that. If we forget to add this 0 here, I mean, we might get the right value or we might get something wrong. Okay, yes, you see we got not 8, but we got 29. So basically, when we go to the thing this points to, it counted until it here ran into this 0, which in this case probably is the stack position of our m length, or maybe something else, of one of those, yeah, of this one. So it really just kept going until it found something that's zero. And of course, this was not desired behavior. So this most of those convenient functions are in fact considered nowadays unsafe. And depending on the compiler configuration, the compiler might even not allow you to do it. So let's see on another. What is it complaining here? Yeah, it's even saying that it might not be zero terminated, but so it's actually quite smart. So let's see what other helper functions we have. And for example, one function that is of course quite useful is something to copy a string. So let's create a larger string. Char my long star. Let's make it a kilobyte in size. We can initialize it to just all zeros, and then star cpy destination source. We could also just write a string in here directly, like this. Oops, not quite like this. So this is also fine, but since we want to use something we already have, we can use this. And if we try now to compile it, you see that it didn't allow us to do it. It says that the function is unsafe, and in fact such string copy, mem copy and comparable functions, when you look historically where most of the different security bugs in C code have emerged from, this is a use of such functions without the proper length checking. So in principle, I mean, if you are using this just with constant strings and you know how long they are, then you take the right value here and it's fine. But as soon as you are constructing a longer string from something that is, for example, a user input, then you might find yourself very easily in a situation where the provided data is longer than the available storage, and then you need a way to somehow gracefully bug out, fail in a defined way, or do something that will not cause memory to be overwritten, which should not be overwritten. So there are of course ways how this can be ignored. So as it even tells us here, we just need to add this definition. Oops, and then the compiler will be happy to accept the usage of this function. As you see here, it copied 1, 2, 3 to our long string, which then that is full zeros. But as said, this is not safe, and such a function really should not be used. So while, for example, strlen is, it might cause some sort of crash if you get the wrong length, you at least know that you are working still with valid memory if you haven't crashed yet, and you just have the wrong length. It did not allow an attacker yet to overwrite anything in your memory, which is the thing that really needs to be avoided. So if an attacker can crash your application, this is not great, but it's also not terrible, because a crash, unless the application is something security critical, like it's controlling the power grid or something, or the pressure in your experiment, and if it crashes, the thing blows up or something like that. But if it's just some application that does something, and if it crashes, it's just crashed, and someone needs to restart it, then it's fine. It's not great, but it's fine. The bad thing is if an attacker is able to overwrite memory inside of your application, especially if it's memory which in some way can then be executed, because then the attacker didn't just disrupt your operations, but potentially was able to take control over your system, and that's really bad. And this string copy or mem copy operations, they have the potential to cause exactly such very bad outcomes. So there is a safe version which is just as appended, and it's pretty much the same thing, just that it takes as an argument the length of our string, and if you would try to write more to it than is permitted, then the operation would just terminate early and not overwrite the memory, which is not allowed to overwrite. So there are of course a few things to consider. This thing is returning error number t type of value. So it will tell you whether it was successful or whether it failed, for example, because of not enough space in the string. And ideally, you should evaluate this value and then handle it accordingly. You would not necessarily want to continue operating with some partial string. So let's simulate such a scenario. So we have a string which only has 5 characters, and in this case, we see that the debug build even throw an assertion. So if we go on repeat, we will see where it came from. It originated somewhere internally, but since we don't have the symbols for those internal C runtime libraries loaded, we are just guided to our own code, and then at this point this thing just crashed as expected. In a release build, those assertions would not be present, but then again a release build might optimize away quite a lot of things. We can quickly see if we see anything in a release build, but in this case we also just get an exception and nothing has been really changed. Let's see what's in this memory here. Yeah, so this just contains some garbage from before but was not even overwritten. So let's go back to our debug build, which creates nicer code. So this is how this works, and let's go back to the proper length. Of course, the next thing one might be interested in is appending text. So if you want to construct some text, copying it is nice. Obviously now you could also, if you want to add some second text, like let's say space 456, you could just and we could go back to the we could do like this. So we have filled this with 8, so we know it's 8 long, so plus 8 minus 8. It's of course not great. Actually, we should really be more diligent about it. Let's go with using the length variable here. Since we counted the length, we can use it. It will at least be somewhat fail-safe. And then we end up with the string test underscore 123 space 456. But of course, this is inconvenient. So there is a struct s function which you can feed the same way as you feed the string copy. But of course now we want to add 456. And it just takes the string, it measures its length, and then it appends this to the end, or it fails, of course, if the length has been exceeded again. And you can just append this string concatenation operations one after the other, as many as you need to construct your final string. It's not convenient, but it works, and there is a huge amount of other convenience functions. It would be a bit too much time to mention all of them, so I will just copy here in a list of the different standard functions. So we have, of course, memcopy is for copying memory. Memmove is also for copying memory, but if the ranges are overlapping, so it can handle this situation. Memcopy requires the ranges to be non-overlapped, and the name of memmove is selected the way because the idea is that you would have a string, and then you would want to move a portion of the string a bit further so that you can insert something inside instead of constructing a completely new string from scratch. And of course, since you are moving characters inside the same memory block, you need something that can handle overlapping memory areas, and that's where memmove comes into play. Then we have already the string copy. Then we have also string ncopy, which allows you to copy a limited count of characters. So we could, for example, use let's see what else we have. String char finds the first occurrence of a string, so we could use string char to find the underscore and then copy only the first portion test into our string using string n, and then we could use string cut to add 456, and it would end with test 456. So there's supplied functions are quite flexible. You can do many things with them. We want like str is for searching inside strings, so we won't be taking a look on all of them, but this is a generally a reasonably complete toolbox that you can use with your string operations. And since they are very basic functions, you can expect any C runtime to be equipped with them. So you will not find yourself in a situation where one of those functions is not available, as long as you are using a C runtime. Now, one thing that is also important to know is that when you work with strings, then you kind of cannot necessarily represent all of them in a simple way. So let's copy this here. Let's call it string2. So for example, you might have a string and you might want to be able to print a new line character, so basically like this. But as you see, this is kind of not valid. And many other, or at least a few other characters are also not valid to be used like this. So in C, you have the concept of escaping a character. So for example, another character is the double quotation mark. You cannot use it since it indicates to the compiler the end of the string. So what you do is you use the backslash character, and then after the backslash character you can specify something else. And of course, if you really want to have a backslash, you would need to use double backslash, and one backslash will escape the other backslash. And this way, of course, for new lines, you would use backslash n, and there are a few other special characters. In principle, if you are creating a string, you might also be interested in writing values which do not exist on the keyboard. So obviously, every character has some integer value, but like the printable ASCII characters the standard ones only go to 127-ish. There are a few control characters at the beginning. There's an extended ASCII set with additional characters up to 225, but you might not have them on your keyboard or any keyboard, so there are ways how you can type them still, for example, by providing backslash x, and then you can provide the hex value of this thing, whatever that would be. So this is how you can do this, and since there are quite a few such escape characters, I will just provide you here with a ready-made list that shows the details. So we have here all the typically available escape sequences and their related byte values. As you can see here, you can also explicitly specify the null character, and in some APIs what they do is, if you want to provide a list of strings, they make a long string, they use \0 to separate the entries inside the list, and once the list is ended, it gets two \0s in a row after each other. So the list can represent most strings, but it cannot represent an empty string, because an empty string is then interpreted as end of list. Of course, this is a workable solution, but again, quite error prone. So if you can do it another way, and there are many other ways how this can be done, that would be recommended. If you can't, then well, then you can't. There are sometimes scenarios where one has to do things in a less elegant way. So the next thing that one of course will think about is, so okay, I can concatenate strings and build them by hand, but if I have an actual integer or floating point or something value, how can I convert it to a string in some convenient way? One approach would of course be to use a function that takes an integer, takes a pointer to a sufficiently long string, and then fills you the one string with an integer, and then you still continue using your concatenation to create the string. But this obviously is quite annoying. So there is a very nice function called sprintf, string printf. Printf means print formatted, and of course _s for security, which then will take a pointer to a string to which to print to and its length, and then it will take a string, a formatted string, And then as you see here, there are these three dots, as we remember from our lecture about variable argument functions. This means that additional arguments are optional. You can provide them whatever you want within certain constraints. So for now, let's just do nothing and just write here test, and we will just end up with a string containing test. So in this case, it behaves like just string copy. It's boring. And it returns, of course, here an integer value. If I recall correctly, it will return the count of characters that it was capable of successfully writing to the buffer. Okay, but let's say we want to append an integer. So for this, we have a whole list of things that we can print. Here a list which is not verbose, but a good start. So an integer would be %i, or you could also use %u if you want unsigned. Oh, that is wrong. That should be %x. Hexadecimal is %x. Yeah. So you could also use %d. That's also like kind of the same thing as integer base 10. There is some redundancy for historic reasons. So %e 1, 2, 3, let's say. And now if we print it, we'll get a string containing containing test 1, 2, 3. So as you see, it replaces. And of course, if you want to get the actually %, you need to type it twice to. It's the same mechanism somehow like with the escape sequences. You have a special character, and if you want to actually this character and not its special function, then you just type it twice. Okay, then what else would be interesting? So let's say we want another string. Sounds useful. 4, 5, 6. Then %s. I will have a space, so let's not give a space here. Then we might want to add a character, an individual character. We can print this as well. %c. This is actually quite useful. For example, you can use it to write the sign of a number, or change the exclamation mark into a dot if you are printing log messages. Many things where it's useful to just change one character. Then let's make a new line, and as we see here, so new line is line feed, and historically, at least on very long time ago, when you were instructing printers what to do, you had really independent operations. You had line feed, which just rolls the paper by one row up, but the printing head stays in the old position. And then you had carriage return, where the printing head, the carriage returns to the beginning of the row. So if you wanted to actually print a new line, you would need to do both \r \n, carriage return and line feed, and then you could print the next row. And in Windows, this is the standard way how Notepad or various other text configuration files are formatted. So if you use the normal Notepad, you will only get, at least the classical Notepad, proper behavior if your text contains both. On Linux, they kind of try to be more modern, and they just drop the \r. They just use \n and nothing else. So in the modern versions of the Notepad, this has been fixed, so that modern Notepad handles both correctly. But if you would have a Notepad, let's say from Windows 7, then I guess Windows 8 as well, then if you would open some Linux configuration file, you would probably see everything in one line and some garbage characters from where line feeds should be. So in our case, since we are here on Windows and we want to be old school, let's go with the full thing, \r \n. Oops, type \r \n. So give us a new line, and then let's say we want to write again test, and let's say we want to write an integer. So integer is %f. You should give a space it, and then of course the integer 1, 2, 3, 4, 5, 6, and let's run it. So one thing we notice here, so let's open this correctly. We see we have our first line, we have our second line as expected. Then we have our floating point number, but as we see here, this is by default always rendered with 6 decimal places of precision. This might be something we might not necessarily want. So we can specify additional parameters to change how it will format the string. We can add .2f, and now when we see what we got, we see that we have instructed it to only provide two decimal places of precision and drop the rest. So our 6 is dropped as well as all the zeros. And by the way, as you see here, we could have much more precision, so we could also have here like .9 to get all the zeros, or maybe 12. I'm not sure how many zeros we actually have here. It looks more like it's 12 zeros. Okay, so what else can we do? We could print some hexadecimal numbers. So let's do this. 0x a b c d e f, and so we add space %x, %x, and again this will then just add this as a hexadecimal number, but as you have seen here, we don't have the 0x before and we don't have any leading zeros. So if we want to add this, we can just first of all just write 0x, that just adds the 0x prefix. It doesn't change the formatting as such, but we can specify that we want, for example, it to be leaded with zeros and want 8 of them, and then hex. So now if we run it, we will always get a hexadecimal value which has 8 places or more if more data would be present. In this case it cannot be, since we are using just a normal 32-bit integer, but if we would be using a 64-bit integer, then we could have twice as many. And yeah, and of course we added the prefix correctly. So, and then let's give you another small cheat sheet with all the different ways how the things here can be modified. So here basically it describes how you can use this format specifiers to define how the numbers will explicitly be formatted, which is quite convenient and good to know. So not everything is demonstrated with everything. So for example, here you see this only with the D format, but it works the same with X. So this is quite generally usable. So, and then of course the next thing that is interesting in 64, my long. Good. So we have a 64-bit integer. If we just print f a 64-bit integer to this thing with %d, it will truncate it. So by default, the things I showed you until now are from the time where you had 32-bit integers at most, and thus all the formatting does this work? It's so let's go with you. And thus the way it works is only capable of handling some of the thing. It is not capable of handling it in its all entirety. So we only have cut a portion of the string. We did not render the whole thing. We could also go with X. Then we will actually see which portion we got. So as you can see here, we only got the lower portion, 0, 9, A, B, C, D, F, and we did not get the higher order bytes, since you guys remember the endianness, they are further back in the memory, so they are just not part of this thing, and by default the compiler will interpret everything here as simply 32-bit. So we need somehow to use another specifier to tell it that this is 64-bit, and we do this with this LL prefix, which stands for long. And now, as you see here, we got the whole thing correctly, and we could also use as integer, so LLU, for example, unsigned, and then we will get the integer representation, the decimal base 10 representation of our string printed here. So this is something that you should remember, because you might work with types like size t, which we have seen when handling arrays and memory, which by default are platform native. So on the 64-bit systems they will be 64-bit, and then your formatting strings will not work correctly. On some platforms you have also special types like %p for pointer, which then automatically evaluates to the pointer type and the right length. So there are quite a few more options here that you might encounter, but since they are platform specific and not a part of the initial definition of C, I won't be showing them here in detail, since for example on an Arduino you might not necessarily have them, and we want to show you here things which are as generic as can be, so that you can use this knowledge everywhere. So okay, so any questions so far? Okay, so if there are no questions, then let's continue. So one thing that of course also is quite interesting is how can you, for example, read in some value from either from the console or from another string, so that you can create so if you have a string provided like our test123, and you might want to get from this thing the value 123 as an integer. There is a function for this as scanf. Oops. As scanf, and then you can provide the string you want to scan. That was but this one is probably okay, because the other one we have edited to add the underscore. So let's go with this one as scanf. Then you provide the formatting. So this should be like %s space %e. I haven't. Usually there are more reliable ways of scanning strings, so this is not something I'm using often. So I hope I remember the format correct. And this thing, of course, doesn't take just variables, but pointers to variables, since it needs to somehow to. So a string is of course already a pointer, so this is fine. But we need for the number int my num some integer, and we will then pass in the reference to it. Okay, let's run it and see what we got. So string now contains test, so it grabbed the test part, the space it saw, and then it grabbed 1, 2, 3 to annum. And of course, if we would have, what do we have? They concatenate something with something. Here we have but we have overwritten this later. So let's just leave it at that. And the thing will return us the count of parameters that it managed to read from the string before it encountered something unexpected. So this is quite convenient and very flexible. So if you want just an integer, there are functions like atoy, which takes just a string, and then the string needs to just only contain this integer, at least the integer at the beginning, and if there is other garbage later on, it might ignore it. But ideally it should just contain only the integer value. So in principle we could go with my num is equals this, and here we would this plus 4, because we know where to find it, and then it will also read us the right value back. But of course this is this only works if you exactly know how your string is formatted. This thing here will work with test or blah or anything, as long as it's conforms to this formatting, while the lower approach would really explicitly require you to know the position where your number starts. So if we know it's space separated, you could use strchar to find space and then split at this position, then use toy, then if you have another entry, use another repetition of the same mechanism, etc., etc. So it gets complicated. It can get complicated quick. Okay, and this much to this. And of course, the next thing one might wonder is, since characters are only 8 bit long, So 8-bit is well, not much, 0 to 255, and we cannot use 0 and a few other control characters which also cannot use. So obviously, while for the uh, Latin languages this is somehow good enough, we have many other languages on the planet which use many different weird characters, or even languages like many Asian ones where you have a character symbolizing, basically a single character symbolizing a whole word. Uh, so how what would one would handle these cases? And the solution to this is just to use a character which is bigger than 1 byte, and this, for example, is a white character. Um, the encoding generally is called Unicode, and the idea is that these characters, generally, and a Unicode character by its definition can be up to 32-bit, meaning you have 4 billion characters available, which is more than enough to represent any character of any language, including the languages where you have characters representing entire words, and then you have still a lot of more free space. So a lot of emojis and stuff like that have also been assigned a Unicode value, so that you don't need to write double point minus close bracket. You can actually just put the right hexadecimal value for an emoji in there, and it will be rendered. On Windows, these values are please excuse me. Sorry about that, I forgot to turn off my phone. Right, so on Windows, these white characters are, however, only 16-bit wide, so they cannot represent all of the Unicode space. But the way they work, they use a so-called UTF-16 encoding, which means that if higher values are needed, then 2 characters are just taken, bunched together, and interpreted as 1. And there is such a thing also for just normal chars called UTF-8 encoding, but it is not natively not supported so easily. So the idea with strings, as you might have noticed, is that it's kind of like an array, so you can easily navigate inside it with offsets. And as soon as you are starting to break up your characters into variable length groups, this breaks. So for example, on Linux, the wide character is 32-bit, and it was like this, I guess, since always. But on Windows, since Windows was so Unix historically was made for huge computers, things with a lot of memory, while the beginnings of Windows were like the IBM PC computers with only a few megabytes of memory. So using as little memory as possible for Windows for their design decisions was very critical, while Unix could afford to go with the clean solutions which consume more memory. And thus, Windows just opted to use natively this UTF-16 encoding, which in some cases is not ideal, but functionally most relevant most relevant things that you want to have Unicode encoded will be just fine in the UTF-16 encoding, and there they will be encoded only using one UTF-16 character. Only if you go towards the more exotic things like emojis and stuff like that, you will need to use words that to use 2 of the Unicode characters to represent one thing that will then be displayed on the screen. And of course, for you as the developer, this is something that you don't really need to interact with, because if you write paths or things like that, they are usually even fine just with characters. And if you want to allow the user to use Unicode paths, then again, it's for the user to input. You don't need to think about it. You just need to provide the right data type, and the operating system, its file picker dialogues, etc., will handle this on its own. And the important thing is that if you will be working with typical basic characters, like for example the backslash as a path separator, this will always be a single character, be that wide char or narrow char. Thus, your parsing functions and things like that won't really care. All those characters which might be encoded as two characters in the UTF-16 representation are non-functional with regard to any sort of usual parsing operations. They will be just contained somewhere inside a string, and that's it. So for you, it will be completely non-issue. So let's see how we can create our first wide string. My best. Well, we obviously do it the same way. But when we want to write it, we need to prefix our string with L before we write the quotation mark test. And let's use our way here to add arbitrary special characters to add something to our string. And let's see what we got. I must have mistyped it. Yeah, I forgot. Wait, U00 1F. It should be right. I have not enough zeros. 3 zeros. 1F6. Should be correct. Yeah, it works. So the preview here is not capable of rendering Unicode characters from the higher values correctly, but if we go on this preview, it shows us that we got some sort of smiley here inserted. And this is quite nice because in this case you really just need one character, although this one will be a bigger one. So UTF-16 one character is only as long as this at the maximum, and here we have already reached the upper level, the situation where it actually needs two characters. So if you would now step through this thing in an increment of one character, this entity here would effectively be two characters, but it is displayed, it is rendered as one. And as said, for most things you will encounter in as wide characters, just stepping one by one will be fine enough. Only in special cases, such very high of such very high values, you will encounter this strangeness. And as said, on Linux, not at all, because there those values, the way they are represented, is 32-bit to begin with. So in a way, it's of course very wasteful, because if you would have some string that only contains ASCII characters, then in memory it will consume 4 times as much memory, because 3 out of 4 characters will be all zeros. So it's, well, not great. And this is why you have often this UTF-8 encoding, because the way it is made, it really only consumes as many bytes as really needed to represent the character. And the nice thing about this UTF-8 and UTF-16 encodings is that most of the standard characters that can be mapped are mapped directly. So like if you have a UTF-8 encoded string, and this string only contains ASCII characters, then it's identical to, then basically it is the same string as ASCII characters. It uses, the way this encoding works is it uses special normally invalid characters to indicate that now some encoding starts. So per character it is a bit more wasteful. If you would have only such characters, then you would end up with a longer string. But if you have a text which usually only contains shorter ASCII characters, then you would have mostly just ASCII characters with some strange things sprinkled along. So this is quite an efficient way of encoding. And let's just for completeness use some svprintf. S maybe. Wait, svprintf, that should be fine. Why is this complaining? It's fine. Just is complaining because we have not provided anything yet. And there should also be the S version, I think. Yeah. And now we need to check whether size of is actually valid, because some of those functions take the count of characters as a limit, and other functions um, take the count of bytes. And usually here, of course, we will want to have the count of bytes, so we can use an, array size. It's not defined. No, that's defined on Windows. Count of. It's also defined somewhere. Let's go with. This should be a. Oops. Count of this one we have. So if we would have included Windows 8, we would have R size available, but we don't, so we go with something built in. This thing will return us the count of elements in the array, and as you might remember from our lecture about arrays, this only works if you have an array that is defined inside the scope, so that the compiler sees the size here, otherwise this will not work correctly. And now, of course, if you want to write some string, we're going to need to provide the L, so that we tell the thing that this is a wide string. Test %s %s. Second %s, as you can see, is a capital, and the way this works is my what was the name? My base string. Just using a small s means a string of the same type. But if you use capital S, it will mean a string of the opposite type, at least on Windows. And this is quite annoying, because on Linux, that's different. In some scenarios, I've seen that you always need capital S for wide strings, and you always need small s for ASCII strings. While on Windows, it's pretty much just swaps. So we can use the same thing the other way around. So just sprintf, not vstring, also not vstring. This is of course short. Then we need to change this to s and this to s for it to work. Right, so this is how you also can easily convert from wide string to normal ASCII string and vice versa. And yeah, and that's that. Any questions? Okay. If there are no questions, then let's quickly take a look on how the Windows NT API handles strings. So they use a structure something like type def struct string so this is basically, we combine a struct with a type def to define also a pointer type. So it's something a bit that nowadays people don't do it like this, but it's part of the Windows API, and it's a bit old school, and it's good enough. So let's keep that. And then we have a unsigned short length, oops, and another unsigned short max length. And as you notice, short, that means it's only up to 64 kilobyte. So the Windows API cannot handle anything that's bigger than 64 kilobyte. But since the API is, well, the NT API at least, is made to be quite low level, you would not want to pass arbitrarily large strings to the kernel, since this would be kind of just wasteful. And for most operations, you only need object names, file names, and other things like this. So the likelihood that you would at some place would need to pass more than 64 kilobit to the kernel is quite unlikely. And then of course, one thing we also need is the buffer itself. And there is this Unicode string. There is also an ASCII version, so there are some APIs that can handle ASCII strings, but generally the whole Windows kernel runs on this UTF-16 encoded white chars. And if you have any functions that would take ASCII, then it's just a convenience function internally that would then still be converted to white characters. since this needs to be consistent. And the way you would use this, let's give you an example, is let's just put in a scope. So we would first define our string, 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 malloc of string. You could of course have also string on the stack, but here let's go with a full pointer. Then you set, then you set length to 0 because well, it starts off empty, obviously. Then you could set maximum length to some value, let's say Caesar of. And important here is that Windows is using as length the actual bytes and not the actual character count. So this is something that one needs to always take into account and multiply by the VHR size. And then we can of course allocate our buffer. Buffer is equals stern malloc. Then we can use already this variable to feed it in here. And voila, we have our string. We can do something with it. And this is a very reliable approach because we always have this max length. So any function by default knows how much it can write to it. And then we of course have the second length, which actually tell us how much of the string is valid. Windows will often generate buffer values which are null terminated, but this is not something you can rely on. They might also be not null terminated. So the length parameter here is critical, and it is what defines it, which also means you can have just here a string which contains null characters and it will be just fine. At least as long as you not try to feed it to some older API that wants a normal C string, then that will not work. And then of course when you want to free it, when you are done with it, you need to free both things independently. And another thing that is quite nice here is that as you might remember about memory management, I explained how it works, that you can just free a pointer and the thing internally knows how many bytes have been freed, basically by somehow storing this size away additionally. And that this is, if you would want to make your own memory management for you, a bit of a challenge, that you need to ensure that if you just free a pointer, that you can then actually know how many bytes in your memory manager to release. And here since we have this max length always, you could implement for your own use case a memory manager which does not in fact will know implicitly how many bytes a particular memory range has, but one which would really just need you to specify starting address and length. Those are much simpler to implement. And then if you are using such strings, you can always just use then this value to tell it how large the thing was to free it. And there is of course to this a bit of a downside, since as you see you need to use two memory allocations and two release operations. So as I mentioned in our lecture about memory, this is not super ideal because each of these operations is quite expensive. So while that is the recommended way how you want to do it, and there is also another advantage of this approach, because you can have your pass string pointer and then you pass it to a function and you can keep this thing null, and then the other function will initialize the whole string. It will create it of the size it needs it, and then you get back something of the right size. But if you are not in such situations, but only in situations where you just need it for your own use and nothing other will be messing with the buffer itself, what you can do is you can just allocate everything in one go. So you just allocate more memory plus let's go like this. See, short. Oops. Unsigned short. Length is equals Caesar of child t. So first we need of course our size. Then we grab this line and we add it. plus length. And then we have basically allocated all the memory we need in one go. So yeah, of course length is 0 because there is nothing in it. Max length is length. Oops. Max length is this length, and a buffer is equals charged, and we need something of length that is a length of 1 per entry, and we call this plus size of string, and this. So we are basically taking the address directly after the whole thing. Then we just cast the whole thing to vchar. And of course, there is another way how this can be done in a bit more elegant way. We just go with +1. So this thing has so if you use pointer arithmetics on this thing, it will do it in an increment of size of string, so it will give us the same value. It will give us basically the first address after our size, and then if we want to deallocate it, we can just free it like this. The downside here, of course, is that you cannot change then the buffer, that you can only kill the whole object. And just for completeness, one more approach that you will often encounter. You just create your string on the stack with dots, and only allocate the buffer from the from the heap, and then of course dot, and this you don't need to. So this way you also have only one memory allocation. It's a bit more flexible, but of course the downside is that then you cannot pass the string to something for keeping. You need to you can pass it, but then it must be stopped being using before you leave the function, as then this memory becomes invalid. Okay, so much to this. So if there are no questions, then let's instantly continue with the next thing. So we'll create a new project for that. Create new project. So we have learned a lot about C now, and now it's time to put our knowledge to some use and create some own structure which will do some non-trivial operation. For example, we could implement a simple list. This is a data structure which is quite useful. It's obvious that when you're working with things, having a list where you can insert elements and remove elements from might be quite nice. Of course, one thing that you could use instead of a list would be an array, as we have seen. We could of course then have an array of structs. Of course, that works just fine, since it's just all memory blocks basically. But the downside, of course, is that if you have an array and you want to insert an element into an array, you need to move all the other elements to make room for the new element. You could work around this, of course, by having an array of pointers and then allocate every individual element individually and put it in there. But then still which is a good approach, but then still you need this array of pointers to be allocated separately and to be managed. So you need to manage its size, its and so on, its lifetime as well. So this also is a bit complicated, and one might want to have some approach how you can create a list in a way that is as simple as possible, and we can do that. So type def struct my entry. So first we define a list entry. And the one thing the entry needs to do is to point to the next thing in the list. And we actually don't add any additional values to the whole thing. We just create a entry that points to the next entry, and nothing is added. We of course need to my entry, finish our type def, my and then of course for our actual list, type def underscore my list. It will have a per my entry per head my list underscore p my list. So the thing is quite simple, but let's add one more member to it. Let's give it a count. So since as you can see here, this will be kind of a chain of entries pointing one to the next, to the next, to the next. If we would want the count, if we don't have a count variable, we would need to go through the whole list and count all entries each time we want to check the length. So this is obviously quite inefficient. Thus, it would not be something we would want to do. So now let's, before we implement the implementation of the list, let's create something that we want, that we would use as a value to be entered there, like say my data, my data, p my data, and the thing needs to have a my entry entry. So as you remember from our structs lecture, if we put this thing, a pointer to this thing and a pointer to this thing, so if we have a pointer to this thing, we can cast it on a pointer to this thing, since this is the first thing, and the beginning will be identical, so this will be fine, and everything that handles just my entry will not care that there are now additional data attached here. So let's attach int data 1, 2, 3, 4, 2, oops, 3 and 4, and now let's create our list, my list, list, and let's use memset, which for which we need to add some. Let's grab those includes, they are useful. So memset is a function which just clears a certain range of memory. So we provide a address where to clear. Technically it doesn't clear, it just overrides with the provided value. So we provide zeros and one zeros, and then size off, so that it knows how many bytes to override. Okay, so we memset the thing, and then we will need some way to insert elements. So let's make a loop where we will be adding 10 things to our list. For int e like 0 is less than 10, e plus plus, and p my data is equals sorry, p my data, p data is equals p my data malloc caesar of p my data. So we have allocated something. We should memset it as well, but this is already a pointer, so it's fine. We could set some of the data to I, so that they are different. The rest we leave at 0, and then we need to somehow add it to a list. For this we will create a helper function. Void insert to list. We could also call it insert to list, and this thing will take a pointer to our list, per list, and a pointer to an entry to be inserted to a list, p entry. And yeah, if you typed if something that is a pointer type, then you don't need to write asterisk. This is basically equivalent to this, but this is the old school way of doing it. So let's keep it. Okay, so let's see how this would operate. But before we do that, let's just quickly invoke it. Reference list, comma, this is already a pointer. Okay, so the idea is that we will just assign to the next thing. So we have our list. Well, first of all, we need to maintain the old value. So we have entry next will be equals to our lists head, and then our lists head will become our entry, and then of course we need to count this plus plus. So as simple as that, and then we can just p data. What is it not happy about? P entry. Yeah, this is now a bit of course annoying because we have here C++, which is doing much more rigorous type checking, and it's complaining. So we could just cast to my entry. This one thing, and the other option would be to do it like this, but effectively it does the same thing. So we just stick with the more low-level approach, just casting here, since we know that this should be fine. And then of course we will want to somehow print the list that we have, so that we see that whether it worked. So for that we create a loop that will be printing stuff. MyPad data. Oops. MyPad data. This is then equals to list.head. Of course we need to cast here, since the list head is the other type. Now we can check if this thing is not null, because it might be null. So if it's not null, we do something, and of course we will need to get to the next entry. So pdata is pdata from the previous elements entry. Okay, in this case, yeah, we need entry punct next. I mean, we could also write this differently. Could go with so we have data. We cast this to pentry punct next, and then we cast next to pdata. So in this case, this is more pretty. This would be the more old school approach. So let's keep with this. And when we are inside here, we can print f. So printf prints to the console, while sprintf prints to a string. So here we don't provide a string where to print to. We just directly start with a format string. %e, and then we just %e, and then we just repeat this 4 times. 1, 2, 3, 4. This one too much. 2, 3, 4, comma data 1, comma 2, 3, 4. 3, 4. You can run it. Right, we should have added a new line probably here, backslash n. DT is not quite right. Did we set it correctly? pdata set size of pdata. That looks like it's right. Pdata should be right. Let's see why is this failing. So we have our data. That data here. Memset is somehow not doing what it should. Oh, sure, there should be not pdata, just data. Oh, this is also wrong. Yeah, no, it's correct. We don't need the breakpoint anymore. Yeah, so this works correctly. One thing you notice, of course, is that the order is reversed, because we're always inserting at the head and then starting from the head. Such a list can be improved by making it double-ended, so that we have not just the pointer at the next element, but also the preview element. And then of course here we would also need not only the head but also the tail of our list. And this will be a homework assignment. What's today? 30, 04, 2026. Um, um, okay, so for this we'll also want another function append to do. So appends to the end, not to the beginning. Update insert to list, append to list. We could insert rename it to prepend, since this is effectively what this is doing. Update prepend, implement append. Yeah. What else would we like to have? We would certainly like to have something that removes an entry. So um, so this will also be a homework. Um, mm, and okay, so this much to this. So we have append, we have remove. We could of course implement a dummy version of append which just goes through the whole list until it finds the end and then appends there, but of course this would be very inefficient, so let's keep here all things efficient. The nice thing about this mechanism here is that since we already have the entry, we can also be very efficient about how we go with removing it from the list. One thing of course that needs to be taken into account is that if it's like the very first thing or the very last thing, then p head or p tail will not p next or p preview will not point to anything but to null, which then indicates to you that if this or this is null, then it means it's the first or the last or the only entry in the list, and then inside the list the head and tail need to be adapted accordingly. There are a bit also other designs which can be made such that you don't need to handle these special cases specially, but here let's go with this, since we also want to update the counter. So to do this you of course need to be able um, to access it. So I can just put here so we don't forget. Okay, and one more thing which is I think quite a nice thing to have is a function. Instead of doing this like here manually, we can put this in a function. Reverse list, which takes a pointer to the list. I mean, we can also make it more elegant. Let's go with void asterisk per list, and now we have a function that will do it. So void asterisk func, and this thing needs an entry and a void sternparam per param and then per param. Okay. grab this. We actually simplified a bit because we don't work with pdata, we work with pentry directly. So this cast we don't need. Those casts we also don't need. So this whole thing is already simple. List pair list head. Right, and here we then use our function pointer. But let's not return any values. That's too complicated. Function pointer, which takes our pdata and takes the optional parameter which we might want to pass to it. Okay, so now this function could be used here. So we have our list. Then we need our, let's say, print comma null. List needs to be a pointer. Then print entry will be a helper function for us. Void print entry. That needs to have the same signature. You can comment this out. By entry, and we leave this p entry. This will be nice this way. Oops. And it will do the same thing. The param could then be used, so it's always passed in, so we could add here something that we could then use here for printing if we are interested in, but we don't need to do that. So this is also quite a nice mechanism. Okay, we have only about 35 minutes left. So I'm contemplating whether we should already start C++ or keep playing with just C things. I think since there are very few people here today because of the different time slot, it would probably be more nice if we start C++ in the next lecture and here keep to just C stuff, and also we don't have that much time, so I guess that will be a reasonable approach. So since let's just create a second project. Zack, create new project, hash table. This will be more just a demo how to do more nice things in just C, and also a demonstration of a different data storage structure. So obviously the array that you already have encountered is quite useful, but it is also somewhat limited, and the list here is a nice additional mechanism that you can use to store data. But what also would be nice would be to have something where you can store data associated with some sort of key, so that then you can retrieve the data in a efficient way. So let's say if you would have a key and value pair and you use an array or a list to store them, each time you want to retrieve an entry from this, you need to go through the whole thing until you find the right entry. So it's terribly inefficient. If you have only a handful of entries, like 5 or 10, it's fine, but as soon as you have hundreds, thousands, or even millions of entries, that gets insanely impractical to find anything in there. So obviously one would want some sort of data storage mechanism which is more efficient, which allows you to find things quickly without having to really go through all the elements. So more scientifically saying, you would want something which has a better scaling behavior than just linear lookup time. Ideally, you would want something that has a logarithmic lookup time, so something where if you increase the size of your data pool by a factor of 2, you would only need one more operation to find what you are looking for. So something of order of log n instead of just order of n in the lookup time. There are also strategies how you can get even better lookup times, like order of 1. Basically, a static lookup time, no matter how many elements you have, finding one element will ideally always take the same amount of time, and obviously it will be a very short time duration. There are two structures which are used for data storage commonly, which fulfill these criteria to some extent in its own way. One is a binary tree. So you have always entries, and then you can go left or right depending on whether the entry is bigger or smaller than the current one. And in such a tree, you get a lookup time of order of log n. So you have this behavior that if you double the data set, you only have to do one more comparison. Basically, you have to take one more branch inside of your tree, since each time you take a branch, you halve the amount of data you need to search in by 50%. And such a binary tree can also be imagined like a sorted list. So if you have a value and you have a sorted list, then you can first, what you do, if you can of course access the list randomly, so it would not be a list like our list but an array. So you have a sorted array, and then you access it in the middle and see, is the value you're looking for bigger or smaller than what I found. If it's if what I found is bigger, then I look in the middle of the first half. Again, is it bigger, is it smaller? Now let's say it's bigger, so then I look in the middle of the second quarter, and each time you have the amount of data you have to uh, interact with. So it's very efficient. And of course, since, as we said, with an array, you have the problem that as soon as you insert something, you need to move all the elements. An alternative data structure is a tree where you have one element at the root which can point to two elements, and each of them can point to two other elements. This sounds simple, but in fact is quite complicated, because while when you have the tree, looking up stuff inside the tree is easy, making the tree to be balanced, so basically that your root is really somewhere in the middle and then you can quickly find things, is quite challenging. There are algorithms how to do that, but first of all, there are a few algorithms. You don't need to always use the same one. The most common one is the red-black tree, but even this is quite complicated, so we will not be implementing this. I just want to mention it so that you know that such structures exist and they are quite convenient to use. Also, we will be using them later on because they are provided as part of the C++ standard template library, so you don't need to know how it works. Or rather, you don't need to know how it's implemented, you'd only need to know what's the working principle behind it. That's that much of this binary trees. The other type, container type that you can use to store data and have a very fast lookup times is a hash table. And these ones are even ideally, in ideal case at least, better than such a binary tree, because in a hash table you have a constant lookup time. So it doesn't matter how many entries you have, you will find what you're looking for always in the same short amount of time. The downside, of course, of the hash table is that it's it with regard to memory management slightly more complicated, and when inserting elements you might need to recreate the hash table, which will mean that the time you need to insert things will not always be the same, but if the table needs to grow, then the time will be bigger. It's hard to say how much bigger, because it will comprise of at least one memory allocation, which has long time, plus might invoke the operating system, so it's not predictable in that sense. A binary tree can be implemented such that you have much more deterministic insert times, but there they are of course dependent of the size of the entire tree, so it's also not ideal in that sense. And the hash table, the good thing about such a hash table is that it is very easy to implement, so we will try to implement it in the available time. So we will first of course need something that will represent our entry, and here let's paste the needed includes. Okay, we don't have them in the list, so let's grab them from here. Zack. Zack. So, as we said, we start with the thing that will store our data. So, type def talked my entry, and this will contain a hash value. So, the idea of this hash table is that whatever key we are using, whether it's an integer, a large integer, sorry, 64-bit integer, or even a whole string, or anything basically, really anything, any sort of memory block we can use as a key, we need to be able to break it down to a hash value. So to a, in this case, 32-bit value, which should have the property that it will try to generate unique values. Obviously, as soon as you have a value which is nominally bigger than your hash value, you cannot avoid collisions. If you have a 64-bit numbers, you will have, for every value of your hash value, 4 billion actual 64-bit values that will all of them give you the same single hash value. So obviously this is not a projection that works both ways, because you are reducing the data set. You are reducing from 64-bit to only 32, or if you have a string that can be a whole page of text, and you are reducing thousands of bits only down to 32. So the trick here is to be able to provide a hash function which will do a good enough job. Why this is important, we'll see shortly. But the important thing is to know that if we have a collision, i.e. two different keys giving us the same value, this will only reduce the performance of our data structure, but will not cause wrong data to be misattributed. Okay, then we have, of course, our stocked my entry p next. Internally, the hash table will be using such a singly linked list as you have already seen in the previous example. My entry, comma, p my entry. And then of course we need our hash table. I'm a bit lazy to type and we are running out of time, so let's speed up a bit with copying things. My table, and my table will contain, of course, a let's be more correct, size t count, u count, small t. I mean, realistically we could just go with integer, but let's go with size t because that's the recommended type. And then we have the thing that gives the hash table its name, a table p my entry. Then it's usually in a hash table you call the thing, so every entry in your internal hash table you call a bucket, and every bucket can contain multiple entries. The idea is that you are using the hash value to find the right bucket, and inside the bucket then you will be actually comparing the actual key, and then only give out values when you find an actual match. And of course, as soon as you are looking up inside the bucket, you go from constant time lookup, because looking it up in an array is constant time, you just add an offset and voila, to going through a list. Thus, you would ideally want a hash table where each bucket contains only one entry. And if your hash function behaves nicely, you can achieve this, at least close to this behavior. If it is not perfect, your hash function, I mean, it will never be fully perfect. So sometimes you might have two entries in a bucket and sometimes an empty bucket. But ideally, this would work such that if you only ever have like a few entries per bucket, the lookup time will be close enough, and then also you can just assume the reasonable worst case of, let's say, 3 entries per bucket, and then assume this as your upper bound for your lookup time. And if you are done faster, then it's of course great, and if not, then well, then not. So next thing, of course, we need is a counter that tells us how large the bucket list is. So bucket array, I should say. And yeah, let's start. So since we want to be quick, let's grab what we need, some this thing. this thing. We will adapt this a bit so that it's faster. This can be still called my data. We have here our entry. Then we'll get some key, char key 25. Let's say you can have 20. Use strings as keys, and then here in our table. So this will of course my table. Then we here zero everything. Then we create our data, but we need to also set the key. So s.f data key, comma test %I, comma e, and then we will have a table add, where we pass a pointer to our table and our new data. And we will also need a hash function. We will need a hash function, and we will need to tell it what the key is. So and pdata reference, or just pdata key. Okay, so let's go void add two things, pair my table, comma, then we have our entry, pa entry, then we have a unsigned intern hash func, which takes a void asterisk key and comma void asterisk key. Pdata, we need to cast this to p entry. Oops, p. Did I call it p entry? My entry. To p my entry, and we need to define a hash function. Let's do it here. Hash function void then key. And we need something reasonable that will give us a good hash value. It's gonna be simple. Int hash is equals 1, 2, 3, 4. So let's go with something just to demonstrate the principle and not something that will really be good. Return hash function for char asterisk ptr is equals char asterisk key asterisk ptr plus plus. So we assume null termination, and here let's take our hash value and XOR it with itself shifted by 8, and the resulting thing, let's XOR it with our single character. That's as trivial hash function as you can get. It's really bad, but it will do its job. For our demonstration purposes, good enough. So let's see what we need inside our add function. So first things first, the hash value needs to be set. So we call our hash function, we give it the key, and it will do the hashing. And then we check if we have enough room in our table. So if p it should be p entry and that should be p table. Oops. So p table bucket count. So if this thing is less than count plus 1, as you remember, we said we want ideally to have one entry per bucket, so we ensure that bucket count is equals or greater actual entry count. In this case, each time we add something, this case will be trend. We will need to grow it, but we can implement a mechanism that grows it by some bigger value, so that we will have some spare space soon. So size bucket array per table, and we added a new size. And let's be smart about it. We don't want to need to do that each time. So first of all, we need a special case. So if this is non-zero, we do this, and else we just go with 8. So, or let's make it maybe nicer. So if this is 0, we just start with 8 entries. And what we do here is we shift everything. Two is too much. 1. We shift everything to the left by 1 position, which is equivalent to a multiplication with 2. And as you might remember, as I mentioned before, multiplications are quite slow, or at least they were slow on all CPUs. Nowadays they just consume a bit more electricity, but it does not really matter. And yeah, and that's that. So we just basically grow our bucket array, resize buckets, let's go it like this, by a factor of 2. And resize buckets, table size t count. Any questions so far? Okay, if there are no questions, then let's continue. So this function will be the most complex function, and it will need a few helper functions. So first we will get a p entry. So the thing is about this function is it will be quite complex. So it will first and it will need to copy all the data around. So what we'll do is we'll convert our array of individual short lists into one long list of everything, and then we will reconstruct a new order from that list. So the way this works is we will have here our head pointer. The count we know implicitly. Now if there is actually something to back up, so if it's the first time, then of course there will be nothing. So buckets then will be null, but if buckets is not null, so later cases we just go through it. For size 10 e is equals pen table bucket count e minus minus comma. So here I just go the other direction so that we will maintain the order inside our list. So as you might imagine, as soon as we enter something to our bucket list, we enter it at the top of each bucket. And if we now serialize everything and then deserialize it, we could of course not care of the order, but we might want to maintain the order at least somewhat, and thus we will do it here in this reverse order. And of course one could just write I greater 0 and this, but I can also Well, not quite. Actually, that would not work because the thing is, we still want to get the zero value correctly. Right. So let's continue. So we take an entry, pair my entry, reference per entry. Is equals. I mean, the reference is already a C++ thing, so let's go with a pointer to this reference on the table buckets. Oops. Buckets at E, and while asterisk p entry and p my entry then next is equals asterisk p entry, oops, asterisk p entry, and then it wasn't right, but that's correct. Next, p next. Now asterisk entry p next is equals p head. You might remember this from our previous case. P head is now equals p entry, and p entry is equals reference. Is it correct? P next. So we take this thing. We have the value. So we have the value of next in here. We want to have the pointer of next. This is not correct, so we need this to be an asterisk with a reference. Right, and then we do this. So the idea is that this way we will be able to modify things inside the thing we are going through. Yeah. Okay. So we have saved everything, and then here we can free the buckets that we had previously. And now we create a new bucket list. Oops. Malloc Caesar of per entry times count. In principle, the function works also to resize it to small. Wait, not p. That's a bug we should not repeat too often. Per entry bucket. Per entry. Wait. This is a pointer, an array of pointers. This was actually not a bug. It was actually correct. Yeah. Fine. So we create this. Then we mem set everything. 2, 0, oops. Okay, we have mem set it. And then we can update our table bucket count to count. And now we need to insert everything back from our list. So while per head per my entry per next is equals per head next. Here we do something, per head is equals per next. And here we add entry to bucket. And this thing takes the entry and the list per table, comma per list. And that's the next thing we need to create. Suck. Okay, I think we will manage to be done in time. Oh, that's not quite right. That's the right name. Okay, so now here we know we have the nice bucket array. We just need to insert the thing into the right position, which sounds easier than it is. So first of all, we need to have an index. So somehow we need to create an index from the hash value. So size t index is equals get index. Again, a helper function we need to make. That thing takes p table and p entry, and the hash value. Size t get bucket index table unsigned int hash. And you know what? Let's do some improvement. Hash t. I hope this doesn't exist already. It might exist. It doesn't. Okay, nice. Int. I mean something. Oops. Something as generic as why is it complaining? Type def structure name hash t. That will be fine. Do I have a typo? I had a typo. Those two have swapped. Right. So instead of having to write unsigned this, we'll just write hash t everywhere where it makes sense. Yeah, nice. Right. So here's our hash. And how do we generate our index from the hash? Well, we want basically to turn a value which might be bigger than the size of our array to a value between 0 and array count minus 1. So we can do it mathematically very easily. Size t index is equals hash modulo operation, so the remainder of a division with the hash should be maybe capital, with the bucket count, and this gives us a value which is 0 and bucket count minus 1, which is exactly what we want as an index. The only downside is this is slow. This is very slow. Well, on old systems at least. So we can be smart about it. If we ensure that our bucket count is always a power of 2, then we can make index is equals hash and binary operation very fast. Hash table count minus 1 semicolon. So this byte operation will give us always values which are 1 less than bucket count. And this is exactly what we want. But this trick only works if when this is a multiple of 2. If it's not, then it won't work. And I guess it's worth benchmarking on your target platform what is faster, because this is still 2 operations, while this is technically just 1. And if the implementation in hardware is particularly good, this might end up faster, although it's highly unlikely. I haven't benchmarked it, but I don't think it will be. And of course, this is then the way to go. So we return our index. So we have here our index. So then we can just insert it. So we go with per entry, per next is equals per table, buckets at index, and buckets at index is equals our per entry. And it's enlisted. We have added it to our hash table And then of course here after the resize, what we forgot now to do is we also of course need to invoke this function. So we already know there is enough room, but with p-entry and not with p-next. And also we should not forget to increment our counter, but as before, this counter is just a convenience counter. It is not operationally significant. The bucket count is what is critical. Okay, and then now of course we want to somehow iterate through our table. So let's since we only have 10 minutes, be as fast as we can. Let's just steal this and that. Hash table data my hash, and here let's this will be the printer. The printer should however also print the key. So key space %s comma comma parent data key. Okay, and the other function, the traverse function, we implement here. This of course takes then my table. This function can remain the same, and now of course the whole thing here will be a bit more convoluted, although we could even have left this in. So, and since we want to be fast, now let's write this from scratch. For size t e is equal to 0 is less than semicolon missing. E is, this is not list but table. Table bucket, hello, m, that should be a pointer. My table bucket count I++. So we go through the whole bucket list, and then here for data we just go with table buckets from I, and each of them is just traversed like the normal thing we had, which then invokes our callback function. So we can now traverse and print our thing. Let's run it. Yeah, it doesn't like sprintf. Let's go with sprintf s, comma size of k. And something's broken because it hanged. Let's see what's wrong. What did here wrong? Let's see. Here we want for the so we want, so this is not correct. Let's see. I don't know, maybe that was wrong. It should have been just the value. But then entry here would be a we don't really need to modify this. This could be just a normal pointer, I think. Let's make it just simpler. I think this should work. Why is entry null? That is not correct. Next was not right. Yeah, we insert here head and not next, of course. And voila. So as you see, the order is kind of random-ish. But it works. And if you would have a lookup function, we should add it since that's the point of this thing. point of our array to be able to find things fast, so we need to add this. Per my entry, find in table, and it should be of course then called traverse table, not traverse list. Right, so we have our find in table. We give to it the table. It will require the hash function. It will require a exact compare function. Asterisk cmp func, which will take a found entry and the void key to compare to, and we of course need a key which we are looking for as such. So then let's add a compare function, ball myCMP func, which takes those arguments. Let's be lazy about it. Return start sample. Per my data on the sorry, without asterisk. P entry. P my should be fine. P my data is defined here at 1 bracket second, 1 P entry, that should be fine. That's broken. Key, comma, we compare with key, and this must be 0 if this is 0 if they're the same. This must be char. Okay, and then let's use the function. So char key equals test5, then per my data per is equals per my data find in table table comma hash func myCMP func comma cmp func comma key my. Okay, that's that, and then we see if we found it. If this is not null, then printf found key. Okay, then we need of course our function implementation. So first we get the hash value, but we just call it hash. Then we get an index, bucket index from hash. Okay, then we traverse that thing for per my enter. We actually have already a traverse code here, so we can grab this. But instead of this needs to know the table to work. But instead of I, we just go with our index that we already have. And now if there are two things that can happen. First of all, even the hash value might not be the same because as you see, we are collapsing the hash space from 32-bit to however many bit we need to represent our thing. So a quick check, a quick comparison is data hash must be equals hash. So this is already a way how we very quickly can bug out without making a lot of string comparisons. And then we check if this is correct, then we use our compare function. Then really see if the thing is what it should be. And if this is true, then we just return our data. And if we haven't found it, then we return null. Right, let's run it. And we found 5. So of course, if we would enter something we don't find, like 0, 5, then we will not find it. And we are out of time, so let's yeah. So I will upload this both things to the Moodle. The homework thing is simple enough. And in the next lecture, we will be learning how C++ works, so the most basic things about object-oriented programming, classes, and so on. And we will use this opportunity to implement our string list as a modern C++ object. And then we will do the same thing as for the hash table, but as a homework. So this should be quite a nice exercise. And then we will continue with other C++ related things. So are there any questions? Okay, if there are no questions, then I will stop the